Morning. Hey, good morning, everyone. We'll get started in another minute or so here. All right. Well, good morning, everyone. Hope everyone had a good weekend. This was Father's Day here in the United States, so it was we had a fun time gathering with family and everything. So that was pretty nice. So I think at this point I've received the prospectus paragraphs and homework number 2 from almost everyone. Young Chow and I will go through everything and we'll get back to you as soon as possible, especially about the prospectus paragraphs and give you any feedback that we see from those. But the couple that I've read already have looked pretty good. So I'll try to get back to you probably today at some point on the prospectus submissions at least. So, okay, and then we'll get homework number 2 back to you hopefully by Wednesday, but we'll see how it goes, and then post the solutions again. Hopefully we'll have a chance to discuss on Wednesday how that looked. Okay, today we're going to start by talking about homework assignment number 3, which is now posted, and then we're going to turn our attention to the analysis of categorical data. So we've talked a little bit about the analysis of proportions already, but we're going to keep building on that today and start getting into bivariate and multivariate analyses of categorical data with our discussion today. So, okay, so to start with homework assignment number 3, this is now posted on Canvas. For this particular homework assignment, there are 3 different exercises from the chapter 6 exercises in second edition of Applied Survey Data Analysis. I'll go through each of those in a second in detail, but I want to mention for the remaining 3 assignments, there's going to be a piece to your final project that you don't have to submit with the homework assignment, but it's kind of a guideline to see where you're at working on the final project. Okay, so again, I want to make that very clear. You don't have to submit an answer to what it says about the final project. This is just for your own reference to see where you and your team should be with respect to progress on the final project. Okay, so while you're working on homework number 3, it says, in addition to completing these 3 exercises, please begin descriptive analyses of the key analysis variables in the data set that you've selected. And remember that you're always going to be referring to your target population when you talk about the results of those descriptive analyses. So you should be preparing some simple tables that present these results, similar to the kinds of tables that you've seen in chapters 5 and 6 of Applied Survey Data Analysis. And again, you don't need to turn this stuff in. It's just to say that when you're making progress, as this week goes along, you should be into descriptive analyses and starting to write about those descriptive analyses in the larger context of your project. And given what we're talking about this week with chi-square tests and comparing estimates between different groups, if that's part of your research objective, you can start playing around with some of those bivariate analyses as well, comparing different groups in terms of key variables that you're looking at. Okay, so that's roughly by the end of this week where you and your team should be in terms of the project. And again, you want to start writing up some of these results as you're going, just at least in very rough draft form, so that you and the rest of your team can go over these points as you're working on the project. Okay, so you'll see these kinds of final project notes on the final 3 assignments, just again to keep you up to speed in terms of the overall 8 weeks and where you should be with preparation of that final project. Okay. Any questions about the project aspect of this? Any questions? Okay, let's turn to the actual exercises then. So the first exercise is ASDA exercise 6.1. So again, this is going to be using the ESS Russian Federation data set, which is on Canvas for you to download in different formats. And you're going to look at a 2-way table analysis involving marital status. That's the variable called MERCAT. And then whether or not someone voted in the last election, which is the variable voted last election. Okay, so those are the 2 variables of interest. And you're going to look at a 2-way table of these 2 variables and make sure to correctly identify and incorporate the sampling error stratum, sampling error cluster, and final survey weight variables in that ESS data set. Okay, you've already had a chance to identify all those. So make sure to use those in your analyses and use the weight that incorporates post-stratification and design features. So use that PSP weight variable when you're actually doing the analyses. Okay, so part A says, what is the value of the Rouse-Scott F statistic for the overall test of the null hypothesis that marital status and voting status are not associated? Okay, so you don't yet really know what that means unless you've done some advanced reading in chapter 6. So we're going to talk about that today. But part A is saying to report that Rouse-Scott design adjusted F statistic along with its degrees of freedom. And I really want to emphasize for part A, remember that a chi-square statistic and an F statistic have different degrees of freedom. Remember that an F statistic has 2 degrees of freedom parameters. A chi-square has 1. So please keep that in mind when answering part A. Okay. Second, under this null hypothesis, what is the p-value for that F reference distribution? And then part C, based on that test, what's your decision regarding the association between marital status and voting behavior in the ESS Russian Federation population? Okay, so it's really just looking at a Rouse-Scott design adjusted test of association and making sense of the results of that test. That's 6.1. Okay, 6.2 then says, repeat the analysis from 6.1, only now performing unconditional subclass analyses for men and women separately. So repeat that test of association from 6.1, but do it separately for men and women, and see if your inferences change when you're talking about men or women as separate subclasses. So really what this question is getting at is there an interaction between gender and marital status in predicting whether or not you voted in the last election? We're kind of doing a stratified subclass analysis. So crucial for 6.2 is going to be using the appropriate subpop commands in the different software when you do that design adjusted chi-square test like we've been talking about. Okay, and we're going to talk about subpopulation analysis in more detail on Wednesday. All right, and then 6.3 says, create an indicator first of high satisfaction with life based on the STF life variable in the ESS data set. And you're recoding that such that values of 9 or 10 get a value of 1, and values between 0 and 8 get a value of 0. So again, this is an indicator of having high satisfaction with life. And remember, be careful about missing values. Okay, so part of that data management is going to be correctly capturing missing values on that ST life variable and making sure they're not being incorrectly recoded into a 1 or a 0. Okay. Then you have these 3 different parts for 6.3. What proportions of the total population and then males and females separately are estimated to have high satisfaction with life? So you're estimating the overall proportion on that 1, 0 variable, and then you're estimating that proportion separately for males and females. Okay, so you should be providing 3 weighted estimates and then design adjusted standard errors for each of those weighted point estimates. Okay. Part B then says compute design-based 95% confidence intervals for these 3 proportions. Okay, and calculate the confidence intervals manually based on the standard errors that you compute. So we're going to talk about different ways to compute 95% confidence intervals for proportions today. So that'll give you an opportunity to practice with that. And then part C says, is there evidence of a significant association between gender and high satisfaction with life? So that's another iteration and another practice exercise in looking at a Rouse-Scott test of the association between gender and that new high satisfaction with life variable that you've been creating. So is there evidence that males or females tend to be more likely to say that they're highly satisfied with their lives in the ESS Russian population? Okay. Okay, so that's 6.1, 6.2, and 6.3. That's the entirety of homework number 3. All right. Okay, any questions then about that homework number 3 assignment? Any questions about those exercises or what you're being asked to do?
I would like to ask about number 6.3.
Yep.
If we are going to get a coding process, can I make it through ACSSD, for example?
Yeah, you can recode in whatever software you'd like. Again, you can use whatever software you want for any aspects of the homework. We would just need to see what code you used in SPSS to do the recoding. Because if we don't see your code and something's wrong with your estimates, we don't know where you went wrong. So when you submit that homework, if you're choosing to use a different software, just make sure to show your code in whatever software you use to do the recoding.
Okay.
Yep.
I saw it.
Yep.
But I didn't put it.
Well, we'll get back to you if there's something that we can't determine what happened. So that's kind of showing your work on the homework.
Okay.
Because if there's an incorrect answer, we don't know why.
Okay, from now on,
Yeah.
with the code, but
It'd be helpful. I know we're not asking for it, but again, it's part of showing your work. Yep, in this context. Yep. Isaac, yep.
So my question is regarding 6.3A.
Yep.
So, is this question is related to subpopulation? You need to declare three populations for total male.
Correct. So total, you don't have to worry about the sub-pop options, but males and females separately you do.
And the second one is designer justice standard. So these are coming from the vaccines.
Right, you're using the standard errors from part A to form 95% confidence intervals. And again, we're going to talk about different ways to do that for proportions today in lecture. Yep, Jones?
On question A under 5.3.
Under 6.3, you mean?
Yes, the one for testing the significance of the difference in proportion.
That's not A. A is just saying report the descriptive estimates. That's all. You don't have to do a test or anything. Yeah, you're just reporting the estimates and their standard errors. That's all. Okay. Other questions about homework number 3? Any other questions about homework 3? Okay. All right, so definitely reach out if you run into any issues or struggles with homework 3. And again, we'll try to get homework 2 back to you in a couple of days here. Okay. If there are no further questions, then let's turn to our topic for today. Oh, and I should mention, as it said in the homework, this is going to be due next Monday. So you have another week to work on homework number 3. That's on the homework assignment. Okay. Okay, let's turn then to module 6, which is going to be analysis methods for categorical data. And arguably, this is probably the most important topic that we'll cover, because the vast majority of analyses of complex sample survey data involve analyses of categorical data. Trying to understand who voted for whom, how many people have a certain disease, how many people have a certain preference, looking at differences between subgroups and these kinds of proportions. Most of the variables that you'll run into in these large national studies are categorical in nature. So it's essential to have a mastery of how to perform these kinds of analyses of categorical data. So we're going to get a lot of practice, a lot of replications this week in how to do these kinds of analyses and make sense of them. Okay, so first and foremost, there's different types of categorical data. You might run into nominal categorical variables. These are variables where the categories are labels and there's no implied metric or ordering of the values on these variables. Things like gender, region, favorite color, political party preference, race, ethnicity, okay? There's nothing crazier than trying to do a descriptive analysis of a variable like race, ethnicity and reporting that the average race, ethnicity is 1.732, right? Doesn't make any sense whatsoever. This is a categorical variable where even though the categories might be coded 1, 2, 3, we still need to calculate proportions in each of those categories, not some kind of overall mean. Or reporting a correlation coefficient between race, ethnicity, and income. Doesn't make any sense because race, ethnicity, although it's coded 1, 2, 3, those are discrete categories with no meaningful ordering. So it doesn't make any sense to report a correlation coefficient between those two variables, because the correlation is designed for continuous variables, okay? So nominal, the values don't mean anything. These are just discrete categories. They can't be ordered in any way, all right? You can't say that one group has a higher mean race ethnicity than another group, right? This doesn't make any sense. And it sounds silly, but we have to be careful about this. Ordinal categorical variables, on the other hand, imply some kind of ordered metric, okay? Things like years of education, grouped underlying continuous variables like age brackets or income brackets, self-reported health, poor, fair, good, very good, excellent. There's an ordering to those values. So the order, the numeric values mean something in terms of how that variable should be interpreted. And again, this is often the case where we recode continuous variables into brackets, where there's an ordering of those brackets. So we'll talk a lot about ordinal variables. And then count variables can be considered a special case of ordinal variables. variables. This is an exact metric. It's the number of times that something has happened. How many times have you been to the doctor in the past 6 months? How many car accidents have you been in since you've been driving? Okay, 1, 2, 3, 4, 5. It's a type of ordinal data, but these are discrete counts. And there are certain kinds of methods that we can use for discrete counts. Okay, so we're going to talk over the next several weeks about different analysis approaches for each type of categorical data. We're starting simple today with univariate and bivariate analyses, but as we get into regression modeling a little bit down the road, we got to think carefully about the right type of model depending on what categorical variable we're talking about. Okay? So it's always important to start there when we're dealing with categorical data. So here's an example of nominal categorical data from the National Comorbidity Survey data set. This is the weighted distribution of US adults by employment category. And the acronym NLF stands for not in the labor force. So that means adults who are not actively seeking employment, they're not looking for employment, so they can't be considered unemployed. They're just not part of the labor force. And so you can see in the US, typically between 0 and 10% are unemployed at any given point in time. A fair number, about a third, are not in the labor force, and the remainder would be considered employed. So this is one of the most common economic indicators that people look at here in the US to see how the economy is doing. What is the actual unemployment rate? And surveys like the NCSR are used to calculate these kinds of weighted estimates. And I underline weighted because it's crucial that we're saying something about the population and that any kind of visual displays that we use, okay, clearly indicate the weighted distribution, not the unweighted distribution. So this is something else to think about with your final projects. Again, at the stage where you should be with development of your final project, if you're starting to think about making figures, make sure that those figures, again, reflect the weighted distributions and not the unweighted distributions, so that that can match with the weighted estimates that you might be reporting. All right, so this is a weighted bar chart showing these distributions. Okay, here's another example. This is drawing data from the health and retirement study in 2012. This is how many times, remember that the HRS target population is people who are approaching retirement age, people who are ages 50 and above. Okay, so we're asking how many times in the past 2 years have you fallen? They had some kind of potential injury from falling down the stairs, tripping over something in the house, falling on a sidewalk, something like that. Okay, and this is just showing those discrete counts. These are weighted estimates of those discrete counts. And this weighted distribution shows something that you often see with rare events that are measured in surveys, a large number of zeros and ones, and then the distribution kind of fades out after that. Okay, so that has implications for what types of regression models we choose for these types of count data. But again, this is a weighted distribution, okay, that shows the distribution of number of falls. You can see there are a small number of cases that have a large number of falls over the past 2 years, but the vast majority are 5 or less in this particular case. So again, it gives us a sense of what's happening in the overall population and potential injury risk with this elderly population. Okay, so graphics, remember, always think about showing weighted plots, especially if you're reporting weighted estimates, so those are consistent with each other. All right, so categorical data analysis, all different kinds of approaches that we could use to analyze categorical data. So we can start with univariate or single variable analyses and tests. So for example, a test of the null hypothesis that a given proportion is equal to some hypothesized value. Okay, how can we go about doing that for a single proportion of interest? Today, we'll be talking about bivariate and multi-way tables involving categorical data. Okay, how can we make sense of those? Log linear models we'll also touch on. These are not as widely implemented in survey analysis software, but this is where we're trying to develop models for the counts in the cells of a given table. Okay, and how we can do that, how we can go about doing that. Logistic models we'll touch on more when we get to regression modeling. So we're going to spend a lot of time talking about logistic regression for binary dependent variables, but also ordinal logistic regression and multinomial logistic regression for ordinal and nominal variables, if we're trying to predict those types of variables. Okay, so that'll be later in the course. And then Poisson and other types of generalized linear models for count data. So we'll touch on those kinds of models as well later in the course. If we're trying to develop a regression model for a variable that captures a discrete count of how many times events have occurred, we'll think about Poisson models or negative binomial models. other types of regression models that we can use specific to that type of dependent variable. So our primary focus today is going to be on univariate and bivariate analyses, and that will lead us into discussion of regression. So if we think about univariate methods, again, graphical display is very important. Okay, so we're trying to communicate with our audiences what the population looks like in terms of distributions on some categorical variable, as in the graphs that I just showed you. And univariate methods primarily involve estimation of proportions and functions of proportions. Okay, so differences between groups in terms of proportions, and are those differences statistically significant? For ordinal and count variables, we might use the types of descriptive statistics that are designed for continuous variables, like means, medians, things like that. But we have to do that with caution. And again, I gave you that example of race ethnicity, which makes no sense. Some fields, if you're looking at something like self-reported health or a level of agreement with some issue, they're okay with reporting something like 2.7. If your field can interpret a mean on an ordinal variable like that, and the different ordinal categories are all separated by the same theoretical amount of value, then that's fine. But just be careful that that mean makes some kind of sense to the people that you're going to be talking to. If a mean of 2.72 on self-rated health is not easy to interpret for anybody in your audience, it'd probably be better to report proportions in each of those categories. So in some sense, there's some tradition, some kind of field-specific norms that involve whether or not you want to report means for ordinal and count variables. Makes a little bit more sense for count variables, because we know each of those possible values is always separated by a count of one event. May not necessarily be the case for ordinal variables, especially if they're based on some kind of recode, where there's different categories depending on how that variable is recoded. Okay? So just I say, use that with caution. It's always the safest bet with ordinal and count variables to think about proportions and report the proportions in each of those categories. So univariate methods in general will involve estimation of proportions, standard errors for those estimated proportions, and then confidence intervals. But we have to be careful with how we compute those confidence intervals. That's going to be another theme today, is making sure that our confidence intervals have good coverage for proportions. And just kind of foreshadowing, the standard confidence interval that we've been talking about so far in the class, the design-based confidence interval, often does not work well for proportions. We're going to talk about alternatives to that standard symmetric 95% confidence interval we've been discussing so far. And then we can also think about goodness of fit tests. So are the proportions that you're estimating consistent with some kind of hypothesized distribution of proportions in your target population of interest? Okay, this is the idea of a goodness of fit test. Are the probabilities based on your observed data consistent with something that you're hypothesizing about a distribution in the population? Okay? So we'll talk about different goodness of fit tests that you can apply for univariate methods as well. So these are all very popular, very common univariate methods, but especially we have to be careful about how confidence intervals are being computed. Yeah. Okay, so here's another example of a plot that you could make based on categorical data. This is an estimated distribution, again, using the weights of United States adults by their hypertension status, okay, which is an issue related to your blood pressure. So there are 4 general recognized categories. You could be of normal status in terms of your blood pressure. You could be considered pre-hypertensive, and then stage 1 hypertensive and stage 2 hypertensive, which is the worst kind in terms of having excessively high blood pressure. So this chart just shows you the relative shares of the US population of adults who fall into each of these categories. And blood pressure is clearly an issue. I mean, this is related to obesity. This is related to BMI. It's an issue. It's a public health issue here in the US, but only about 2.4% are considered to fall into that worst category, at least based on the 2011-2012 NHANES. And this is something that people analyzing NHANES data track regularly. Every time a new NHANES cycle is released, what is the population looking like in terms of this important indicator of other health problems? So key point again, this kind of pie chart, if you choose to go that route, is weighted, not unweighted, when you're showing this kind of distribution. Okay, so when we're talking about univariate or single variable analyses of categorical data, this involves estimation of these simple proportions. And we've already seen this formula before. This looks just like what we've been talking about with a weighted mean. Okay? The difference here is that we're talking about an indicator variable of being in a particular group in the data set. So that's what that I means. That I means that you're part of group 1 in general on this kind of proportion. And we're just calculating the weighted sum of that indicator in the numerator divided by the sum of weights in the denominator. Okay? So in other words, a proportion is the estimated size of the population falling into a particular category divided by the total estimated size of the population. That gives us a weighted estimate of that proportion. And again, we can just express that as a ratio of 2 estimated totals, just like we talked about with the weighted mean. So there's nothing really new there. The proportion is simply the mean of a 1-0 variable, okay, that we've created in the data set. So that's nothing new. Given that it's a ratio of 2 estimated totals, we can use the exact same linearized approximation for the variance of that estimated proportion. This formula as well is no different from what we've seen in previous discussions of linearization. Okay? We need the variance of an estimated total. We already know what P is based on our weighted estimate. Okay? We need the covariance of those 2 estimated totals. And then we just need to plug in that estimated total for the size of the population in the denominator. So same formula we saw for the weighted mean, no different. Okay? Now, what is tricky when you're dealing with proportions and writing papers and writing reports that use proportions, you don't want to flip back and forth interchangeably between percentages and proportions in the way you're talking about this. So remember, a percent is 100 times the estimated proportion. And you can see the formulas here for converting the standard errors back and forth between one another. I'm not going to care, Young Child's not going to care if you report your results in terms of proportions or percentages. You can go either way. Just make sure to be consistent when you're writing about your results. If you start talking about a percentage here, keep talking about percentages in your tables, your graphs, throughout the rest of the paper. Don't label a proportion a percentage, okay, because those are 2 different things and that can really confuse people. Okay, so just be consistent in the types that you're reporting. And you can use these conversions to go back and forth between the different standard errors. Okay, confidence intervals. For single variables, this is the method that we've been talking about so far in the class. We have the weighted estimate of the proportion plus or minus the critical t-value times the standard error of that estimated proportion. That's the standard, what we call walled type or asymptotic normal confidence interval. And this is the default approach used by SVY mean and SVY ratio within Stata. Okay, so those particular commands within Stata will use that default symmetric confidence interval approach for proportions specifically. Okay, but that general approach of calculating the estimated proportion and symmetrically adding or subtracting that critical t-value times the standard error has very poor coverage properties for proportions. Okay, so put differently, if you say that you're computing a 95% confidence interval, there's no guarantee that that interval is going to cover the true proportion 95% of the time, okay, when you're working with proportions. And generally, we want to consider alternatives to this confidence interval, especially for proportions that are very low or very high. A simple point that I alluded to before the lecture today is if you have a very low proportion or a very high proportion, and you're again forming the symmetric confidence interval in this way, the lower limit might fall below 0, or the upper limit might fall above 1. And we would never want to report that as being a plausible value for a proportion, because proportions are bounded between 1 and 0. So when we're forming confidence intervals for these types of proportions, especially for very rare phenomena in a population, we have to rethink how we're computing those confidence intervals and the relative coverage of those intervals as well. So yes, while we could use survey mean or survey ratio to do these kinds of analyses, it's generally much safer to use other approaches to form these confidence intervals. So one possible method of computing these confidence intervals is called the logit transform method. Okay? And this is actually the default that's used by SVY tab and SVY prop within Stata when you're dealing with complex samples. Okay, so they default to this logit approach. And the SVY CI prop function with an R, this is why within the survey package, there's an entire function dedicated just to confidence intervals for proportions, is to give you options to calculate these confidence intervals as you're going through. So if you wanted to use the method of the logit transform in SVY-CI prop, you can use method equals logit in quotes, but there are other methods you can specify as part of SVY-CI prop. That function is specifically there so that you're not just always defaulting to the standard walled type interval that we've been talking about in the class so far. We want to consider alternatives that have better coverage properties. That's key here. Okay. So here's how the logit transform works. Once you have your estimated proportion and you have your linearized standard error or your jackknife standard error or whatever approach you're using, you calculate the limits on the logit scale or the log odds in the way that you see here. Okay, so ln of p divided by 1 minus p, this is also known as the log odds. That's going to be very important when we talk about logistic regression. That's like your left-hand side variable when you're fitting a logistic regression model. So that's the logit transformation of that estimated proportion. Okay, and then we're multiplying the critical t value times the standard error of the proportion itself divided by p times 1 minus p. That's the standard error on the logit scale. Okay, so we already have those inputs to start with. We form the interval on the logit scale to start with. So I'm just referring to those two upper and lower limits as A and B in general. Once we've computed those, we apply an inverse logit transformation to get back to the probability scale. So once we have A and once we have B, we exponentiate A and divide by 1 plus the exponential of A. That gives us our lower limit. And then we take the same thing to the B component. That gives us our upper limit. The key property of this approach is that logit transformation ensures that both limits stay between 0 and 1. Okay? There's no guarantee that these intervals are going to be symmetric, like the walled interval, but we ensure that those two limits stay between 0 and 1, which is the property that we really want for these proportions. Now, that approach has better coverage than the standard symmetric walled interval, but not the best. There are still better approaches yet that are out there. We bring this up to begin with because it's the default in most of these procedures. So when you're talking about how confidence intervals for proportions were formed in your reports, in your scientific papers, and so forth, you do have to be clear about which method was used to form those intervals, because there are non-negligible differences that can occur depending on what confidence interval approach you use. Okay? So this is something else that's important about the methods that you might be reporting in a paper or in a write-up more generally. All right, so let's just look at the difference here. This is an example that's looking at confidence intervals for proportions. Looking at the dependent variable, it's a regular heartbeat in the NHANES. So that's our variable of interest. We want to estimate the proportion with an irregular heartbeat in the NHANES target population, again, as a potential indicator of other health issues or heart issues down the road. And we're focusing on adults who are ages 18 and above in this particular analysis, because the younger children were not given this measurement in the NHANES. Okay? So this is again using NHANES 2011, 2012. This was a variable that was measured during the physical examination. So we need to make sure that we're using the exam weight when doing these analyses. We use the survey set command we've been talking about thus far. Cluster codes first, probability weight second, in square brackets, the exam weight there, and then the stratum codes third as the straight argument. Okay. Then we're showing 3 different ways that an analyst might go about doing this analysis. Okay. First way, we might use survey tab. Okay. Notice all 3 of the different approaches, we're always using that unconditional subpop analysis. We're using that explicit subpop option. We're not deleting the kids. Okay. We're creating a 1-0 variable in the data set called age 18p. We're using that subpop option explicitly. It doesn't matter which of these approaches we use. Okay. First command tab, we simply list the variable of interest, irregular, and then after a comma, those are all options that I want to see in the cells of that analysis. So standard error, confidence interval, column proportion, okay, even though we're not looking at 2 variables, this will become relevant when we talk about bivariate analyses, and then depth for design effects. So those are all options that we can provide as part of SVY tab to enrich the output that we're looking at. Okay. Second alternative, we use SVY prop or SVY proportion, okay, to get estimates of that proportion in addition to its standard error and its confidence intervals. All we do there is say SVY prop and again the name of the variable, regular. Okay. Third option, we might just use SVY mean because we're literally just taking the mean of a 1, 0 variable. Okay. It's another way we can get the same point estimate just like we did with proportion. Okay. Now let's look at the differences. All three sets of output here, 5,374 cases analyzed. That's our unweighted sample size. 17 degrees of freedom, 31 minus 14 like we saw in the lab. The point estimates of the proportion are all identical. Okay, those should not change. Just like we talked about with the variance estimation method, depending on the way you actually compute that weighted estimate, we're using the same formula. All three of these procedures are using the same formula to get the point estimates. Okay. Linearized standard error, fully adjusting for the complex sampling features also does not change. Okay, we're using linearization in each case. We're applying the same linearized approximation. We should see the same values. Doesn't matter depending on the command that we're using. What changes slightly in this case, but still does change, are the confidence intervals. That's where we have different approaches to computing these confidence intervals. So both tab and prop are using the logit transform technique that we just talked about. Okay, mean is using that standard symmetric walled type interval where we just add or subtract t times the standard error. Now in this case, you'll note the intervals don't look that different from each other, but notice that the logit transform approaches shift the interval away from 0. Okay, again, that's part of a transformation that's designed to keep those values between 0 and 1. So that's why you see a slight shift away from 0 when using that logit transform technique. So in this case, the walled interval wouldn't do that much of a problem. Okay, we see that the standard error is pretty small for this particular estimate. But if you had a really rare proportion with a large standard error, using that walled interval can become problematic. And so the logit technique shifts it away from 0. And every single point estimate here has the same design effect. Very modest 1.21, so 21% inflation in the variance associated with this particular point estimate. Okay? So there's not that big of a variance inflation due to the complex sampling features. And we'd be okay if we just use SVY mean, but that's not always going to be the case. And again, the coverage can suffer of that symmetric interval. Yep, go ahead.
Linearized SE is the default and have not specified whether it is the jackknife or Taylor series of the comment.
Yeah, remember in Stata, linearization is the default. So if we don't specify anything in any of the code, linearization will be used by default.
So if we need to change it to another one, we have to add the jackknife or the.
Right, so in the survey command, we would say like subpop AJTP, but again, before the colon, we might say VCE jackknife or something like that, if we wanted to do that on the fly. But in the NHANES, we're given those stratum and cluster codes for the purpose of variance estimation. So we're fine just using linearization as it is. Yep. The key point in this example is the change in the confidence intervals. Okay, other questions about this code or the output? Yep, Isaac.
So we have like two so that is for the lower bounds.
Yep.
0, 1, 3 and the 0.01.
Right.
This is because just the change of the logic transformation.
Right. Yeah, the logit transformation is shifting those limits away from 0. Yep. And again, there's no guarantee that the logit transformation is going to give you a symmetric interval. Like if you look at those intervals and you look at the difference between the point estimate and the limit, if we go to the lower side, the difference is about 0.0032. If we go to the upper side, the difference is 0.0040. So it's not symmetric. Okay, but that's okay. The key point with forming these intervals is that you have the stated level of coverage. If you simulate, you look at the coverage of these confidence intervals across many hypothetical samples, that property of having 95% coverage is much more important than whether or not the interval is symmetrical. And so logit transformation is not going to give you symmetric intervals for the most part. Okay. Other questions about this example? Okay, here is the corresponding R code. Okay. So remember in R that if you want a variable to be treated as categorical, you need to declare it to be a factor variable. You can either do that when forming the data frame, or you can do that on the fly in the analysis commands by simply wrapping that variable in the factor function. So when we use a factor variable in SVY mean, that ensures that SVY mean is going to report proportions and not means. Okay, remember that's, we have to use that approach of using SVY mean and factor variables to get estimates of proportions within the survey package. Okay, so sub n Haynes is a design object that was formed using the subset function for people who are age 18 and above. So we talked about that procedure on Friday. Okay, and then we're asking for the standard error. We're removing missing values. We're asking for a design effect, and we're asking for a confidence interval. All as a part of SVY mean. Same options that we had in survey tab within Stata. Okay. Then after we create this object, so another way, instead of just looking at the output, you can save the essential information from that analysis in a new object in R. So this is how I usually operate within R, is I work with these objects that contain the results of the analyses. Once I have that object, I don't have to keep writing that function over and over again. If I, for example, want to compute a confidence interval, I can just refer to that particular object. Okay, so that's what I'm doing here to get the confidence interval. Confint by default will give you that walled type symmetric interval. Confident is just taking the standard errors, taking the critical t values, and forming that symmetric walled type interval. That's what the default, what the confint function will do. In survey, again, we have this SVY CI prop function available specifically for this problem. Okay, and so here's the version of SVY CI prop that I would use to calculate that logit transform interval for that proportion of those within a regular heartbeat. Okay, this would exactly match with what SVY tab and SVY prop are doing within Stata, is using SVY CI prop in this way with method equal to logit. So that function all at once is going to give us our estimate, our standard error, and the 95% confidence interval. And I'm using SVY CI prop. Okay, so that's a good function for those of you who are using R. That's a good function to become familiar with when you're dealing with this kind of descriptive estimation, is SVY CI prop. And I'm going to talk about some others. Once again, I'm saving the results of that analysis in a new variable called X, or a new object called X61P. And then I can look at that new object, I can run other analyses on it, and so forth. I think that's a little bit more efficient way to work within R, is to save the results of your analyses in these new objects that you can then do other things with. Okay? But that's how we would replicate what we just did within Stata. Questions about the R code here? Everybody comfortable with this? Okay. Now, recently, there have been additional simulation studies that have been examining this problem in more detail. This is an entire paper that I was fortunate enough to referee dedicated to this question. What's the best interval for a proportion estimated based on survey data? It sounds like a very simple question, but this is an entire paper about it. So this came out in 2019 in the Journal of Survey Statistics and Methodology. And one of the biggest takeaway message from this most recent simulation study that's been performed is how poorly those symmetric confidence intervals perform in terms of coverage when you're dealing with data from complex samples. Okay, probably the biggest takeaway message: it's a bad idea to continuously compute these symmetric confidence intervals for proportions. Okay, biggest takeaway message. So they evaluated via simulation a number of different ways of computing these confidence intervals, including the logit transform method that we've talked about. And they show that the logit transformation helps. It increases coverage relative to the symmetric interval that we're talking about, but it's not the best version that's out there. Over the years, many different individuals have written approaches to calculating confidence intervals for complex samples that have improved coverage. What Carolina Franco and her co-authors did in this particular case is they did a systematic evaluation of all these different intervals that have been proposed, and they evaluated some of their own new intervals that they were proposing that they hypothesized would have better performance, better coverage than yet all these others that were out there. okay? And what they demonstrated was that some of these intervals do in fact have substantially improved coverage properties relative to some of these other more traditional types of confidence intervals that have been created. So up on Canvas, I'll show you where this is, in the readings folder. You are going to find this variable here, I'm sorry, this R script here, it's called CIARR capital FCN.R. So when I was refereeing this paper, right, they did this awesome simulation study. And to do a simulation study, right, you have to write the code to implement your methods, right? So they did this great simulation study, showed all these interesting results about these different intervals, and didn't provide any code. I said, guys, like Rod Little. Some of you met Rod Little. He's one of the co-authors on this paper. I said, guys, just give people your code, right? You're making this huge argument about how it's a bad idea to compute intervals using the default method that most software is using. Here are the better ways to do it. You've done the simulation. You already have the code. Just show people your code. So we had a back and forth with the editor of JSSAM, and finally the editor agreed and said, okay, guys, provide this code. This CIARR FCN is just the raw background calculation of each of these confidence intervals, still pretty hard to use. They kind of gave in and said, okay, fine. Here's the code. It's not that well annotated. You know, it's not super easy to use. So what we did, you're going to find another R script a little bit farther down here. This R script called Franco et al. 2019.R. This is actually carrying out a realistic analysis of the ESS data set, calling that other set of functions. Okay, so this guy is the one that you can use to actually replicate the analyses to a point where when you calculate the confidence intervals, that code is going to spit out every possible interval that they evaluated in that paper. So for a given analysis of a proportion, that Franco et al. Will give you the symmetric interval, it'll give you the logit transform, and then it'll give you like 8 others. And there were some of those others that they argued have the best coverage in these situations. So our general recommendation, as you can take a look at that code, is to just look for a given analysis, whether or not your inferences would change substantially across these different intervals, and see if you need to report one of those adjusted intervals that are talked about in that paper. We're going to look at that in the lab on Friday, but just keep in mind that this code is up there, but you have to use this pair of R scripts in order to do this. Unfortunately, they only wrote their code for R. So you're not going to find this in Stata. In Stata, you have to rely on that logit transform and just kind of cross your fingers. Okay? But there are better methods out there. Unfortunately, to date, they've only been programmed in R. Okay? Hopefully, someday, someone from Stata is going to take that calculation approaches in that Franco et al. Paper and just program them as options within survey tab or survey prop, but it hasn't happened yet. Right? So to be thorough, our recommendation is just to run that Franco et al. Code for a given descriptive analysis and see if anything changes, depending on the intervals that you're following. Okay, so we'll come back to that on Friday. All right, so I want to point that out, that's up in the readings folder. And again, the recommendation is to see whether your inferences would change when computing these to supplement kind of the default confidence intervals that you might be computing for a given proportion. Now, if your proportion's 0.4, 0.5, 0.6 for whatever you're studying in the middle of that range, these intervals are not going to vary that much. Okay, your inferences are going to be very similar. Again, this is a bigger deal when you have small or large proportions. Okay, here's the reference. This is also up on Canvas if you want to take a look at this particular paper. Okay, so that's a single binary variable we've been talking about so far. If you're dealing with a multinomial variable, so many categories, like I said, race, ethnicity, region, political party preference, favorite color, whatever it might be, estimation really doesn't change. You're just creating multiple binary variables for all of those different categories, right? And then you're repeating that calculation of a weighted proportion for each of those different binary variables. So I sub k here is just an indicator variable of belonging to category K. on a multinomial variable. Other than that, this looks like the same formula that we've seen for weighted means and weighted proportions. Okay, so that's what the software is doing in the background for multinomial variables. It's just creating new indicator variables for each of those categories and then calculating weighted proportions based on each of those indicators. So we'd want to make 100% sure that these weighted estimates sum to 1 when we're doing this analysis. If these weighted estimates do not sum to 1, we have a problem. Okay, there's something wrong about the data management, or maybe it was a missing data issue or something like that, but these should sum to 1 because we're describing the overall distribution in a population. Okay, so nothing different kind of mechanically there. For multinomial variables, again, you can do variance estimation by linearization or by some replication method. Because again, essentially, we're just dealing with weighted estimates of proportions, nothing different. Okay. Again, survey tab and survey prop are going to use the logit transform method by default. But something that's new about this kind of analysis is the possibility of doing a goodness of fit test. Okay, so you have an entire distribution of proportions on some variable of interest, and you want to see if that distribution is consistent with something that you're hypothesizing about the population. Okay, so maybe you believe there's a certain distribution of political party preference in the population, and you calculate your weighted estimates of all those proportions, and you want to see if that vector of estimates is consistent with something you're hypothesizing about the population. That's where you can do this goodness of fit test. But the goodness of fit test has to adjust for the complex sampling features. That's the key thing here. And that's what we're going to be talking about with chi-square analysis. So a user of Stata wrote an article for the Stata Journal where they said, okay, here's how we can do a design adjusted version of this one variable goodness of fit test. Okay, some of you might think of this as a chi-square test for simple random samples. Here's how we can do it to adjust for complex sampling features. And that methodology is implemented in a user-written command for Stata. So this is not part of base data. This is a user-written command called MGOF, multinomial goodness of fit, okay, that we can download and then use as a supplement to our analyses if you wish to test hypotheses like this. Okay, so we're going to see how to use that. All right, so let's look at this example of estimating proportions for multinomial variables. Again, using Stata here, the variable of interest is blood pressure category, like what we saw in the pie chart. Okay? So we have these 4 categories: normal, pre-hypertension, stage 1 hypertension, stage 2 hypertension. We could argue that this variable is ordinal in nature, right? Because the ordered values, we can order them in some way. The values are meaningful. We're going to treat it like multinomial for now, just for this particular example. But we could certainly argue this is an ordinal variable. Okay? So we set our design features like we did for the previous example. This is another exam variable. So you got to make sure to use that exam weight within NHANES. Okay? Now we're using tab specifically here just so we have access to all these different options. Prop doesn't give us as many options. Okay, so with using tab in SVY, we have access to all these different options here. All right, so the variable of interest is BP cat for blood pressure category. Again, we're doing unconditional analysis of this subpopulation with that age 18P indicator. And then we're asking for 4 options in the first tab command. The observed count. OBS will show you the unweighted count in each of those cells. So that's where you would get the sample size that you want to report for this kind of analysis. That's going to give you the unweighted sample sizes, OBS. Then get your linearized standard errors, okay, by default. You get your logit confidence intervals, because that's the default confidence interval construction technique that SVY tab is using. And then column proportions. Again, irrelevant here just because we have one variable. That'll become more relevant when we talk about two-way tables. Now, tab only allows for 4 options at a time. So if you want additional output, we run that second version of the tab command. You're going to see all the same analysis, same estimates, everything else. We're just using that to get the design effects as well, just because we can't put 5 options on the same one. Okay? Nothing different about that command. So that generates the table that you see below. For each of these 4 categories on this variable, you see the unweighted sample size. That's what OBS gave us. You see the weighted estimates of the proportions. And again, we want to make sure that those weighted estimates sum to 1, okay, across the board. Otherwise, something's off in the way they've been computed. Okay, so we see, for example, we estimate that 47.2% of the population would be in the normal hypertension category. Okay, depending on who works at the CDC here in the US, that might be good news or it might be bad news. Okay, a lot of people have written papers comparing NHANES cycles to each other over time to see how these things are changing in the US population. Okay, we see our linearized standard errors for each of the 4 proportions, okay, based on the linearization technique, and then those logit 95% confidence intervals, right? Then we also see the design effects. And again, the design effects are changing for each of these different statistics. Okay, it's a property of what we're trying to estimate, okay, not the survey itself. And we see the general pattern like we talked about last week, where the larger the sample size for that particular group, the higher the design effect, because we have a larger cluster size on average for that particular outcome, but not all the time, right? Look at stage 1 hypertension, stage 2 hypertension, there the design effects flip somewhat. What that tells us about stage 2 hypertension is that the values on that indicator variable are tightly clustered in the US. So there are pockets of people that have stage 2 hypertension all in a particular area. Okay, it's not widely distributed across the US. It's highly clustered. That's why the design effect is so much larger for that variable, even though the sample size is smaller for that particular outcome. Remember, that design effect is going to be a function of the average sample size per cluster and that row quantity. In this case, for stage 2 hypertension, row is very large, a very tightly clustered feature in the US. Okay, all these design effects are fairly large, but we see relatively narrow logit intervals regardless. Okay, we still have pretty good estimates of each of these proportions. Okay, questions about generation of the descriptive estimates here to begin with? Any questions about this before we look at the goodness of fit? Everybody good on this, the code and the interpretation? Again, 47.2% of the population is estimated to be normal, not the sample, not the respondents. 47.2% of the population is estimated to be in that category. Remember to use that language. We've got to get out of the habit of saying X% of the respondents or X% of the sample. We now have the luxury, because we're doing weighted estimation, of making statements about the population. Okay, it's crucial. All right, here's the corresponding R code. Again, we would use survey mean in combination with the factor version of that particular 4-category variable to generate each of the individual estimates and the corresponding confidence intervals. And again, we could use SVY CI prop if we wish to, the way that we're forming the interval. You'll be able to practice with that on your homework. Okay. Now, we'll talk about this goodness of fit test and then take a break here. So here, what we're looking at is a null hypothesis in the ESS data set about the distribution of marital status among individuals age 15 and above in Russia. Okay, so now we have a 3-category variable. Okay, before we had a 4-category variable, and we want to test a null hypothesis that the individuals in Russia follow a certain distribution in terms of marital status. And we want to see if our weighted estimates are consistent with that null hypothesis distribution. We're using that MGOF user written command in Stata in order to do this. Okay. Now, first thing we do as part of this analysis is we create a variable that contains the null hypothesis values in the data set. And we do that via this recode command here. What we're doing is we're recoding the categorical variable of interest in Stata, where we say for category 1, the null hypothesis value is 0.5. So we're hypothesizing that 50% of the population is in category 1. Category 2 on marital status, we're hypothesizing that 25% of the population is in category 2. And notice these are written as proportions in this case. Category 3, that's the remainder, right? We hypothesize that 25% of the population is in category 3. And based on that recode, we're generating a new variable called pi. That new variable in the Stata data set is simply going to take on those values depending on what category you're in. It's just going to be a constant set of values for each of those categories. That's all it is. That's a required input for using this function. Okay. Now, once we've downloaded and installed that user written MGOF command within Stata. We can then run the command MGOF, and to test the null hypothesis, we say that the variable of interest Meerkat equals that variable containing all the null hypothesized values that we just created. So we say MGOF Meerkat equals pi, and then after a comma, we add the SVY option. What that's going to do is read in all the essential information that was declared in survey set previously. I didn't show the command here, but we've seen that command multiple times for the ESS at this point. Okay? So once that survey set has declared these design variables globally, adding SVY calls on each of those design variables for this user written command. Okay, so that's going to carry out this test that Jan in this 2008 article created for complex sample survey data. Okay, this was the article I was referring to in the Stata Journal. So there's a couple different goodness of fit tests that will be performed. You see the design adjusted F statistic that's being computed for each of these, and then the corresponding p-value. Now, how do we make sense of that p-value? The null hypothesis is that the weighted estimates fit the hypothesized values well. Okay? So we want to fail to reject the null hypothesis in the case of a goodness of fit test. Okay? The null is that those proportions hold for the target population. If we reject that null, we're saying that we have a different set of estimates relative to what the null hypothesis is going to say. There's a big enough difference where we have evidence against that distribution holding for the population. So in this case, with that p-value of 0.19, we're failing to reject the null hypothesis, which is what we want in the case of a goodness of fit test. That means that our weighted estimates are in line with what we're hypothesizing about the proportion. So given this result, we can say that it's entirely plausible that the distribution of marital status in Russia at the time of this data collection is 0.5, 0.25, 0.25, as we would have set out. If we rejected that, we would say we have evidence against that hypothesized distribution. Okay? And the key thing is F statistic and p-value fully adjust for all those complex sampling features when we're doing that analysis. Okay, that's the important thing here. Okay, so that can be very useful for testing those kinds of hypotheses. Up here.
So, like, Professor, if we reject the overall goodness of fit test,
Yep.
for example, reject everything, can we then find out which category yeah.
Yeah, not exactly. Like you can see where the biggest deviation is just by comparing your weighted estimates to each of those hypothesized values. But that test is not going to point to one category as being the culprit. It's just saying that overall, there's not enough evidence here to say that that distribution holds. So you could easily report and say, well, it looks like the biggest difference is in terms of category 2, but the overall test is just talking about the overall consistency. That's it. Yep. Yep. Other questions about this approach? It's like I talked about with the Franco et al. Article, only available in R. This MGOF, only available in Stata. I'll say some things like people over the years have asked Lumley, well, why isn't this available in survey, or why isn't this available in survey? And he's literally a one-man operation. So this is an example of something that, yes, he could program this if he wanted to. He just hasn't yet. He's writing free software. He's doing it without the support of a grant or anything like that. He's literally maintaining survey in his free time. Okay? So not everything's going to be programmed everywhere, but this is an example of something that's only in Stata. Okay, so I think this is a good natural point for a break. It's about 10:06 on my watch, so let's break until about 10:11. And then when we come back, I'm going to pick up with bivariate analyses. So far we've been talking about single variable analyses, and we're going to talk about looking at associations between categorical variables for the remainder of the class today. Okay, so let's break until about 10:11, and I will pick back up at that point. All right, thanks everybody.
I tried to. I'm following you, writing this up. Option not allowed all time, but then when I run.
You don't have the data set. There's no data. Oh, you do, okay. Oh, so you were just at the end.
But when I'm going to write this one option is not allowed, but then so I next one works. For example, option is not allowed.
I have no idea why it's saying that. It's something, it's somehow confused with options, like there was a blank indicated as an option at some point. I don't know if you were copying and pasting, but it's trying to read in another character.
I tried to.
Yeah,
I tried to.
you gotta restart Stata and start from scratch to the point where you're not getting that error message. Otherwise, there's gonna be kind of ripple effects in every other command that you're running. So just, I would try restarting and then rerunning those things, because that user written command is, if it can't find the survey characters easily or the survey features easily, then it's not gonna work.
Okay, طب what about slide number 18 here?
Slide.
Number 18. Sorry, 19. Yes, for recording.
Yep.
Why we are going to make one equal, or I know that we are going to need it for MG.
Yeah, that's your hypothesized values. I made those up. So that's up to you. Yeah. So that you're hypothesizing that the distribution of marital status is 0.5, 0.25, 0.25. That's up to you.
Okay,
So
and
that-
if we have 4 categories.
Then it's up to you, right? You just have to make sure those hypothesized values sum to 1. So you might think that for the 4 categories, it was 0.75, 0.5, 0.1, 0.1. That's entirely up to you.
Okay, the last question is,
Yep.
when I'm going to make the last one, MG I install the package already.
Yep. Yep, looks good.
And then I'm going to do this. Maybe because I have to.
Well, it says that you need this piece too. I'm not sure why that wasn't installed, but you just have to run that as well.
Oh, I have to run this.
So then, I don't know why it's asking you for that in particular, but once that's installed, that error should.
Okay, I will try
Give that a
to.
try.
But we have another option using the.
Yeah, you can use however many categories you want. It's just that whatever those proportions are is entirely up to you.
Thank you.
Yep.
Okay.
Oh my God.
Okay, yeah. Right, yeah. Developers. Okay.
Yeah, thank you. I didn't see that.
Yeah. Yeah, why? It's a magic number. Yeah. You have to understand.
Sigma?
Sigma.
American Nicole. Okay.
Yes. I was supposed to be able to.
probably went home already. Oh, well. It's not a night.
Yeah, the both teams are going back.
Ah, shit. What do you think of this?
Or like, maybe there's a chance. Another option. Or like, maybe. But then,
No, like, what they say, the boys are, I don't know how they.
maybe the West Indies. So, it's
Oh, they were
maybe. But they're, it's like.
Yeah. Yeah.
Like,
And some football, you say, all around.
All right, so we left off talking about univariate analysis. Now we're going to shift gears and talk about bivariate analysis, where the goal is to talk about associations between two categorical variables rather than just describing distributions on a single variable. Okay? So crucial to these kinds of bivariate analyses is the construction of what are called contingency tables or cross tabulations. And there's different ways that we can communicate the information in these kinds of contingency tables or cross tabulations. We could talk about total proportions, or we could talk about row or column proportions. And we're going to talk about the distinction between those two different kinds of estimates because they are very different from each other. Okay. We're going to talk about hypothesis tests of independence. Okay, so how do we test hypotheses that different variables are in fact independent of each other and when we're dealing with categorical data. We'll talk about calculation of odds ratios and relative risk ratios, okay, and the important distinction between those two kinds of measures of association. We'll talk about simple logit models and also odds ratios as part of these descriptive analyses. And then again, later on in the class, we're going to talk about regression models as multivariable methods, going above and beyond just a single predictor of a categorical outcome. Okay, so for now, the focus is going to be on bivariate. So again, visualization, very important for describing these kinds of associations. Okay, it's easy to report tables and these kinds of chi-square tests and so forth, but it's always helpful to have some kind of visual, especially when we're trying to describe what's going on in a larger population. So this is an example of a clustered bar chart that shows you separately for males and females what the distributions are on that 4-category blood pressure status variable within the NHANES. Okay, so you can see the estimated distribution for males looks pretty different from the estimated distribution for females, especially with respect to how many individuals are pre-hypertensive as opposed to normal. Okay, so there's some visual evidence here, given that these are weighted population estimates. There's some visual evidence here that males and females do in fact have different distributions on this blood pressure status variable in the US. Okay, so that's one way you could show these kinds of bivariate associations. There are certainly others. But again, the key here is that this is an estimated distribution based on the use of weights, okay, to create those that cluster bar chart. So Let's look at an example based on the National Comorbidity Survey where we're looking at a 2x2 table to start with, just to keep things pretty simple. So in this example, suppose that we're interested in studying the association between gender, which in this case just has 2 categories for the data set we're working with, and then a lifetime major depression episode. So there's an actual clinical diagnosis coming from the survey of whether or not you qualify as having had a lifetime major depression episode. Okay, so based on the questions asked in the survey, we can come up with an indicator of whether or not you've ever experienced this in your lifetime. And the goal of looking at the 2x2 table is to see if there's an association between gender and this binary indicator, right? That's our kind of research objective here. So in this kind of 2x2 table, again, there are several proportions that we might be interested in, okay? One example is a total proportion. So this says of everyone in the population, what's the probability of belonging to a particular cell in this table? Okay, that's the definition of a total proportion. Some people think of this as a cross classification. Okay? If we were to divide the population up into all the groups defined by the cells in this table and estimate what fraction of the population falls into each cell, that would be the total proportion. Okay? So it said all of those total proportions are going to sum to 1 in the entire table that we're forming. And the notation here says, for example, what's the estimated count of the population that's in cell A0? So they have value A on one variable and 0 on the other variable. Divided by that n hat plus plus, that's the size of the entire population across all the cells. Okay? So those are total proportions. Very, very different quantity is a row proportion. This says of all the people in a given row of the table, what fraction fall into a certain column? Okay, so of all the males in the population, what fraction have ever had a major depressive episode? It is quite different from the total proportion. And we'll see an example of that coming up here. It's again crucial when you're dealing with categorical data to keep these quantities very separate because they mean very different things. Okay? It might sound very simple right now, but it's very easy to make this mistake, okay, when we're trying to describe populations. And then a column proportion is the same idea, defined by the table. We say of all the people in the population in a given column, what fraction fall into a particular row? So of all the people who have ever had a major depressive episode, what fraction are males? Okay? That also very different from the first 2 types of proportions that I've talked about here. All 3 of those are wildly different estimates. It's important that we keep them very separate when we're talking about interpreting these kinds of results. So we'll see examples of this kind of interpretation. Okay, so in the NCSR, here's an example of looking at this 2x2 table and then computing both the total proportions and row proportions. Okay? So here's how we go about doing that. First of all, declare the design variables for the NCSR. The cluster codes, the short weight, because this variable is measured for everybody in the survey, not the subset that was given part 2 of the survey. So we're using the short weight that was available for everybody. And then the stratum codes. Okay, so we declare our design variables. Now, so far, we've been talking about using SVY tab for single variable analyses. Now we're doing a 2 variable or bivariate analysis. So the way that SVY tab works, the first variable listed is the row variable in your table. The second variable listed is the column variable defining your table. So what we're saying is that sex defines the rows, males and females. MDE defines the columns. So this is going to form that 2x2 table, and we're computing weighted estimates of the total proportions in that 2x2 table. That's the default when you use survey tab. Okay. So as options, I want to see the linearized standard error. I want to see the 95% confidence interval based on the logit transform, and I want to see the design effects. Those are my options. If I don't add a row or a column option, survey tab will default to giving me total proportions. You just have to keep this straight. Otherwise, you could really be misleading your audience. about what you're talking about this association. Okay. If I want row or column proportions, I simply need to add row or COL, like we saw in the previous code. And now the 2x2 table shown by Stata will give me those row or column proportions, if that's what I actually want to report to describe this association. Okay. I tend to personally prefer reporting row proportions. I think kind of left to right in these tables, I say, if you have this value on a predictor, what's the probability of having this value on the outcome variable? I like to think about these associations in that way. Other people might want to report total proportions. You just have to make a decision as the analyst, what's going to best answer your research question. Okay? So here are the two different sets of output reported. We're going to spend a little bit of time talking about these because it's so important to keep them distinct. Okay. In the total proportion example, the first SVY tab command, remember, you're splitting the entire population up into these 4 groups. And then you're estimating the proportion of the population in each of these 4 groups. So those guys sum to 1 for those total proportions. So looking at these estimates, we would say, for example, that 40.6% of the population is a male that's never had a major depressive episode. Okay. We're creating 4 groups. I'm just saying what percentage of the population falls into each of those 4 groups. That's what the total proportions are giving you. Okay. I see a linearized standard error for each of those 4 proportions, the logit transform 95% confidence interval, and then the corresponding design effects. Look what we see in the column of the design effects. Who can interpret that 4th design effect for me? What is that telling us? The 4th design effect of 0.81, what is that telling us? Is it better? So the complex sample is giving us a better standard error, right? Relative to a simple random sample of the same size, the complex sample is giving us a more efficient estimate. That is the very definition of a win-win, right? Because we're saving money and we're getting a more efficient estimate. Why would that be the case? What about the design is going to result in a design effect that drops below 1? Remember, let's go back to that picture we talked about with design effects. Remember that tug of war that we discussed? What about the design is going to drop that design effect below 1? Stratification. This is an example where the stratified design of the NCSR for that particular estimate won the tug of war. The G, the gains in efficiency from the stratification, overwhelmed any inflation in variance due to the cluster sampling or the variability in the weights. So it does happen now and then. Now, the sampling statistician's dream is that every single design effect is less than 1, right? It's never going to be the case. But for some kinds of estimates, this can happen. And this is one example, okay, where the G for stratification wins. That empirical battle, if you will. Okay, so let's just look at that 4th proportion just to drive this point home. We would say that we estimate that 12% of US adults are females who have had a major depressive episode. Okay, that's that category of the overall population with a very precise estimate introduced by the complex sample design. So those are the total proportions. Let's look now at the row proportions and how we would interpret those. Okay, so the goal of our analysis is really to compare males and females in terms of the probability of having had a major depressive episode. The total proportions don't really shed a whole lot of light on that association. They're just giving us the overall cross-classification of the population. Row proportions say specifically, if you're a male, what's the probability of having had a major depressive episode? Okay, we can answer that. The estimated proportion of males who have ever had a major depressive episode is 15.1%. Notice that 15.1% is very different from 7.2%. Those are very different quantities. Okay? In one case, we're conditioning on being a male and saying, what's the distribution of MDE? In the other case, we're just reporting the total proportion of the population that falls into a particular cell. They're very different, and we don't want to get those confused. Okay? So to answer our research question, we can say, okay, we estimate that 15.1% of males have ever had a major depressive episode. Let's look at females. If we condition on being a female, we estimate that 23% of females have ever had a major depressive episode. Eyeball test says, wow, that's a big difference. Okay? But we need some kind of formal test of whether or not those proportions are different from each other. Okay? But just based on the descriptive analysis, definitely seems like those guys are different. There's a higher risk for females. Okay? But we want to do that more formally. Okay?
This one, the first one is down with the maybe have major depression. Divided by the total.
Right, that's saying 7.2% of the entire population is defined by males who have had a major depressive episode. Here we're saying that if you're a male, the probability of having MDE is 15.151. Okay, and again, for the row proportions, we see the same phenomenon. For the male row proportion, that design effect is 0.87, it's less than 1. So the NCSR sample design was a win-win in that regard, in terms of the stratification being especially effective. Okay? Questions about this initial descriptive contingency table and the distinction between these kinds of proportions? Any questions about this? Okay. All right, so this is just showing how those weighted estimates of the total proportions, if you were actually going to report this table, this is showing how the weighted estimates sum to 1. Okay, this is just taking those values from the previous output table and reporting them in the 2x2 table format. Okay, so this is again dividing the population into 4 groups and then estimating the proportion of the population in each of those 4 groups. Okay, that's how we might report that.
Sorry,
Yep.
I should have asked before. And the last, the other slide. Why the dish for women were so bad at best compared to women?
For that subpopulation, the stratification was effective. So for females specifically, if you were to look at these proportions, their values across all the strata, there's a ton of variability. And that between stratum variance, as we know, is being thrown out. So for women in particular, the stratification was especially effective. Yep, that's what's driving this. Yep. And so, right, that's like I said, the goal of the sampling statistician is to come up with a design where that between stratum variance is huge, no matter what variable you're talking about, no matter what subpopulation you're talking about. It's a dream ideal. You're never going to get there, but it does work once in a while. That's the idea. Yep, Jones.
How do we calculate the column proportion?
Right, column proportions. So those aren't shown in this table. So I don't have the estimates, but I'll make them up, for example. Okay. So if you had column proportions, you would say, of those who have a major depressive episode, right, 60% are females. So you flip it around, you condition on being in one of the 2 column values. So you say, if my objective in interpreting this association is to find out what fraction of people with a particular condition are males or females, I would interpret the column proportion. If my goal was to compare males and females in terms of that probability, I'd use the row proportions. It all depends on your objective and what question you want to answer. So if I wanted to characterize all the people who have ever had a major depressive episode, I'd probably look at the column proportions. And again, I don't know exactly what those are in this example, but that would be the kind of interpretation you say of everybody who's ever had a major depressive episode, 60% are females. Something like that. So that's something you can play around with on your homework. And again, as you're getting into your final projects, just try adding that row, try adding that column option, and just interpret what you see. Just practice. Yeah. Okay. Okay, here's how you might display the row proportions, right? Same 2x2 table, same data, just different estimates that we're using to describe that association. So this makes it a little bit clearer that there's a higher risk for women as opposed to men in terms of ever having had a major depressive episode in the US population here, okay? Key thing about those row proportions, they sum to 1 in each row. Okay? Instead of adding up to 1 for the entire population, like we saw for total proportions, the row proportions will add up to 1 in each of the rows. So it's always a quick check that you're reporting the right thing. Okay, now again, I like to think of it as the row variable being the predictor, the column variable being the outcome in these kinds of tests of association. More generally, you could use a logistic or a polytomist, also known as a multinomial regression model, to analyze categorical data where you have a clearly defined dependent variable and you have a clearly defined predictor variable. Okay, you can use regression models in that general setting. But a lot of times we're only interested in this kind of bivariate association. Is there evidence that these two categorical variables are associated with each other in some way? So a very common test that you learn in Stats 101 is the chi-square test. Okay? So use the chi-square test to see if there's evidence of an association between two categorical variables. The null hypothesis is that those two variables are independent of each other. Okay, so what you get in the contingency table, it doesn't matter what row you belong to, you're going to see the same row proportions. Okay? So that's what you learn about early on. And we want to see if the data are consistent with that null hypothesis of independence or if there's evidence of a stronger association than that null hypothesis would suggest. Okay? So for a 2x2 table, so for the case we're looking at right now, under this null hypothesis of independence, we could do a test where you want to see if these two variables are independent. That's one way of thinking about this null hypothesis. So under the null hypothesis, we can write down the expected proportion in row R, column C of that table as simply being the product of the proportion in row R overall and the proportion in column C overall. That's how we define that null hypothesis of independence. If the data that we have are consistent with that idea, that equation there, then it suggests that the null hypothesis holds and those two variables are independent. Right? So that's another way to write it is in terms of expected counts in row R and column C. That's just rewriting the same thing. Okay? For a 2x2 table, another way that we could frame that null hypothesis of independence is as a test of a difference in those two proportions. Are those two proportions equal to each other? Okay, so if your sex is equal to R, is the probability of depression equal to the probability of depression if sex is equal to R prime? Okay, are those two different from each other? Same idea. It's speaking to the exact same test. We just want to see if these two variables are independent of each other. That's two different ways of writing the same null hypothesis in the case of a 2x2 table. More generally, 3x3, 3x4, whatever the case may be, we frame the null hypothesis as part 1, a general case of independence of the two variables. Okay, so what you learn about in Stats 101 is this idea of the Pearson chi-square test, named after a very famous statistician. The chi-square test statistic basically is a measure of the distance between the expected and the observed counts in the cells that define that table. Right? So you look at what you actually observe in each of the cells, you look at what's expected under that null hypothesis of independence, and you essentially sum up all those standardized differences. They're really squared differences in this case, but you sum up all those differences, and then you see how big collectively those differences are. That's the idea of the chi-square statistic. So if those differences are all very small, and the observed proportions are close to being equal to the expected proportions, you don't have a lot of evidence against your null hypothesis, and it seems like independence will hold. But if those observed differences are big, those square differences are big, then you have evidence against the null hypothesis. You have a larger chi-square value, and you might reject that null hypothesis. Okay? The likelihood ratio is a related type of test that you can use to test that same null hypothesis. And the likelihood ratio boils down to essentially the same thing. How similar are the observed proportions to the expected proportions. Just another way of writing the same idea, basically. Okay? So both of those can be used to test that null hypothesis of independence. But again, it's a distance measure. The bigger that distance measure, the more different the observed proportions are from what's expected under the null hypothesis. Okay? That's the way the basic chi-square works under simple random sampling. Okay? So about the 1980s, late 1970s, late 1980s, people up to that point have been applying that standard Pearson chi-square test to data from these kinds of complex samples. And statisticians started to question that practice, and they started to develop design adjustments that would give you more powerful test statistics reflecting these complex sample design features. So the question that they were trying to address was, how can we incorporate the design features into this standard Pearson chi-square test? Because so many people are using it. And we know that ignoring design features can add bias to estimates and can affect estimates of association. So there's got to be a better way to do this, right? So there were two approaches that grew up in the 1980s. Ivan Filegi, from Canada, first of all talked about correcting the standard Pearson chi-square statistic that was based on simple random sampling. And I'll talk about how that works in a second. But then J.N.K. Rao and Alastair Scott, J.N.K. Rao was visiting Alastair Scott in the early 1980s. He had a visiting professorship out at, I believe it was out at Southampton. And they had lunch. They said, yeah, we know Filegi's working on this approach. I think we can do better. I think there's a better test statistic out there that does a better job of incorporating these design effects. They literally had lunch and they sketched this out. Okay. They wrote a paper in 1984. It came out in the journal Biometrica, which is the origin of what's now known as the Rao-Scott test. The Rao-Scott test, even today, 40 years later, is still the standard for doing design-adjusted tests of association between categorical variables. All came from a lunchtime discussion. Okay? Still the standard. And they later in the 1980s developed better approximations for this test that, again, gave analysts more power in testing that null hypothesis. Okay, so these were very important developments around that time period. So what Filegi was first thinking about was look at the average design effect of all those proportions that are involved in calculating that chi-square statistic, all those distance measures. So for example, for the 4 proportions that define the 2x2 table for the NCSR example, the average design effect was about 1.24. If you go back to that previous slide. Okay? So take that average design effect and divide the simple random sample Pearson chi-square test by that average design effect. So Filegi showed that when you divide the actual Pearson chi-square by that average design effect, you still get a statistic that follows a chi-square distribution. So you can still base your test on that scaled chi-square statistic, scaling by the design effect. What else have we scaled by the design effect previously in the class? What other formula did we divide something by the design effect to get something else? Effective sample size. This is the same idea, right? Remember, we took the nominal sample size, we divided by the design effect, that gives us our effective sample size. This is giving us our effective chi-square. This is the same idea. So it was a nice idea, very simple to calculate to begin with. We obtain a p-value for that scaled chi-square by referring it to a chi-square with r-1 times c-1 degrees of freedom, just like you learn about in Stats 101. So that was Filegi's contribution. Here's how we can deal with the design effects in this kind of analysis. Okay, very easy to implement in the different software. Okay, what Rao and Scott talked about over lunch was taking more advantage of the different design features, and can you come up with something that better approximates a true distribution than that scaled chi-square? That's the idea of the most powerful test statistic. Okay, that was approximately chi-square, what Filegi showed. Rao and Scott said, we think we can do that. Give you a more powerful test statistic. So what Rao and Scott said, let's use the weighted proportions to form our overall chi-square. It makes sense, right? We want unbiased estimates of each of those proportions. But on top of that, they said, we believe the test statistic should follow an F distribution. And that F statistic is going to give you a more powerful test of that null hypothesis of independence. The question is, how do we get to that more powerful test statistic? They showed that rather than just dividing by the simple average of the design effects, you should divide that chi-square by what's called a generalized design effect. It's a more complicated measure analytically, but that division by the generalized design effect gives you a more powerful test statistic for testing that null hypothesis. That was their main contribution. That generalized design effect is the average of the eigenvalues of a matrix that I'm about to show you. If you have no idea what an eigenvalue is, don't worry about it. Okay? Essentially, it's another version of the average design effect that gives you a better test statistic for this test of independence. And again, nowadays, Stata, R, SAS, Sudan, they all default to this Rao-Scott adjustment approach because it gives you a more powerful test. Okay? So here's how this basically works. Remember the idea of the design effect for a given estimate. We take the variance of that estimate under the complex sampling, divide it by the variance of that same estimate under a simple random sample of the same size. What Rao and Scott said is that you should leverage the generalized design effects that come from this particular design effect matrix. Not for an individual estimate, but for a matrix based on the estimate. So you take the variance covariance matrix of all of those proportions under the complex sample design, all their variances, all their covariances under linearization, jackknifing, whatever. So we would have a 4x4 matrix for that 2x2 table, right? 4 proportions, 4 variances, and then all the covariances off the diagonal. There'd be 6. Okay. Then you multiply that by the inverse of that same variance covariance matrix under a simple random sample of the same size. It's the same basic idea. You're just talking about a matrix rather than an individual estimate. 4 variances, 6 covariances under simple random sample. What Rao and Scott showed is that using the average of the eigenvalues from this particular D matrix gives you a better design effect rescaling. It gives you that more powerful test statistic. That was their chief contribution. Okay. So taking the mean of those eigenvalues, or what you can think of as being a better version of the average design effect, you take that standard Pearson chi-square based on the weighted estimates of the proportions, and you divide it by that generalized design effect based on this design effect matrix. That gives you what's called a first order Rao-Scott correction. And that's the default in SAS, for example, when you're using Proc Survey Freak, is you get this first order design effect correction, okay, called G, that we're calling GDEF here. You can, we'll see the formula here in a second. You would use the same scaling of the likelihood ratio chi-square. Okay, same idea here, but using the weighted proportions as input. Okay. Now, what Rao, Scott, and Thomas later in the 1980s showed is that, yes, this follows a chi-square distribution, this rescaled chi-square, but we can do even better based on this second order correction. Okay. You think about, there's 4 design effects, right, in the 2x2 table. Taking the mean is one way to summarize that distribution of design effects. What is it not telling us about the distribution of the design effects if we only use the mean to summarize that distribution? What are we not learning about that distribution of design effects? Here?
Variance.
The variance. So what Rao and Scott said was, well, let's not just focus on the mean. Let's also figure out a way of accounting for the variability in those design effects, right? One design effect might be like 1.2. Then you might have this other design effect that's like 6.3. So the scaling factor should itself be scaled by how variable those design effects are, right? One mean of 3.3, if every single design effect is 3.3, that's a very different situation from a mean of 3.3 where one design effect is 1 and another is 8, right? So they said, let's also account for how variable those design effects are. This is this second order correction, which is actually what Stata uses by default. This is a second order correction where you scale that generalized design effect by 1 plus the squared coefficient of variation of those eigenvalues. Long-winded way of saying how variable are those design effects. Okay? That's that 1 plus a squared scaling factor. Okay? Where else have we seen 1 plus the squared coefficient of variation? Where else has that popped up in the class so far? Where else did we see that in terms of design effects?
interclass?
Close. It was part of our discussion of design effects. But where else do we see 1 plus the squared coefficient of variation? Remember 1 plus L? When talking about variance inflation due to weighting. That L, remember, was the squared coefficient of variation. Same basic idea here. The Kish was using to talk about variance inflation. That's part of the issue here. That 1 plus L factor, when we talk about the eigenvalues themselves, is the same type of variance inflation that they wanted to account for in this second order correction. Okay. So take that generalized design effect, divide by 1 plus the squared coefficient of variation, you get a second order Rao-Scott chi-square, or likelihood ratio chi-square. Okay, you don't have to do any of this work. The software is doing it all for you. Okay, it's just important to be aware of what's being reported by the software that you're using. Okay, now in SAS, you actually have to request the second order correction as an option in Proc Survey Free. In Stata and in R, the second order Rao-Scott correction is reported automatically when you do these tests. Again, because it's more powerful. I don't know why SAS does it that way. Okay, but it does have to come up as an option, or you specify it as an option. This is the whole gory formula for calculating that generalized design effect. And this is for a 2x2, I'm sorry, a two-way table of proportions. This is where you get that actual design effect measure that you're using in the scaling. Again, pretty complicated analytically. The key thing to recognize from the whole calculation is that it's primarily a function of those design effects. That's the primary idea here. We're using the design effects of all the proportions, defining that individual table. So don't worry about committing that to memory or anything. It's just an important part of the correction in this case. So under that first order Rao-Scott chi-square, taking the Pearson chi-square, dividing it by the generalized design effect, like Falegi showed, we again have a chi-square distribution with R minus 1 times C minus 1 degrees of freedom. So again, that was very simple to implement analytically. What they also showed, and this is basically a known result in statistics, if you take that chi-square, divide it by its degrees of freedom, you get an F distribution. Okay? So they said, better to report this overall F distribution, which just takes that adjusted Rao-Scott chi-square and divides it by its degrees of freedom. Here, that resulting F statistic has 2 degrees of freedom parameters again. Numerator is R minus 1 times C minus 1. Denominator is R minus 1 times C minus 1 times S. Here's where the design degrees of freedom come into play in this overall test. And again, that's what Rao and Scott showed. This would give you a more powerful test that's adjusting for the design degrees of freedom than just reporting the simple chi-square in this case. So they were in a constant quest to find that most powerful test statistic in this case, right? So that's what we're going to use moving forward. And the important thing to recognize is that you shouldn't be kind of scratching your head and asking questions when you see the software reporting an F test or this test of association. That's where the idea of seeing an F statistic comes from when testing these kinds of hypotheses. Is this derivation that Rao and Scott went through to show what kind of distribution this test statistic follows. Okay, so we're going to see that as part of the output. All right, so default in Stata, second order Rao-Scott test, default in SAS, I should say in R as well. Default in SAS, first order. So if you want to see the second order again, you have to add an option, and we can look at that in lab on Friday. Okay, nice thing about Stata, you don't even have to do anything. Survey tab prints that second order Rao-Scott test automatically. You don't even have to put in an option. If you specify 2 variables, you get the test by default. They make it, again, mindlessly simple to do this stuff the right way. Okay? So let's see how this works. In Stata with the NCSR, this research question is seeing whether or not there's an association between education and alcohol dependence among young adults specifically. Okay? So among young adults, does it seem like there's a link between how much education you've obtained and whether or not you've been diagnosed with alcohol dependence, okay, during this time period of life, all right? That's the research question that we're looking at here with this design adjusted test, all right? So here's how we would set this up in Stata. Same as before, set the design variables globally from the NCSR using the short weight. Okay. Now look at how I specified the subpop unconditionally. I'm interested in young adults between the ages of 18 and 28. So in this case, I'm setting up an if condition. I'm saying if age is greater than or equal to 18 and age is less than 29. It's kind of an on-the-fly subpopulation that I want to use for this analysis. Alternatively, I could have just created that indicator variable and specified it as a part of subpop if I was going to do more stuff with this subpopulation. Okay. Then, once I have that subpop, my command is tab for doing these two-way tables. Row variable first, that's education, add for cat. Column variable second, that's this indicator of being diagnosed with alcohol dependence. Again, based on this clinical diagnostic interview that they conducted in the NCSR. All right, so that's my table, my two-way table. Then I add 4 options. I want to see row percentages to help me interpret this association. I want to see my linearized standard errors. I want to see these logit confidence intervals, and I want to see my design effects. Okay, those are the 4 options that I use to enhance what's shown in each cell of that corresponding table. Okay. All right, nothing that says Rouse-Scott, nothing that says chi-square, Stata prints it automatically when you have a two-way tabulation. Okay. All right, what do we do in R? In R, we start with SVY by to create these proportions that define the overall contingency table. This is if you want row proportions. Okay. The SVY table function will give you total proportions. If you want to see row proportions, you have to set that up as doing an analysis of the binary variable separate for each category of your row variable, which in this case is education. So what I'm using is SVY by, where ALD is the binary variable of interest. Okay. Add for cat is my categorical factor defining the rows. Notice my subset. Okay. Here I'm specifying the unconditional subpop on the fly. Taking my original design object, this NCSR SVYP2 is my original design object. I'm subsetting it to age being less than 29 and not being missing, okay, on any of these other 2 variables. Okay, so that gives me my unconditional setup. My analysis function is SVY mean. I'm taking out missing values and I'm asking for confidence intervals as a part of that overall analysis. So that's giving me my row proportions that would define the table. But I don't get the Rouse-Scott test automatically by doing that. That's just the descriptive piece of the overall table. To get the Rouse-Scott test, I have to use SVY chi-square. So that's a new function we haven't talked about yet. Okay, another function that's available in the survey package. Okay, that gives us these design-adjusted Rouse-Scott tests of independence. So to set up this kind of test, I use a tilde. First variable is my column variable, so it's a little bit backwards relative to Stata, plus my row variable, education. Okay, so important to get that kind of ordering right there. Also important to remember the tilde before we set up that combination of variables here. Same subset to do my unconditional subpop analysis, same removal of missing values, but then I say statistic equals F. So by default, it's going to give you that Rouse-Scott chi-square. If I want to see the F that Stata is producing automatically, I do have to add that statistic equals F option. Okay, gives you a more powerful test. So now both of these sets of commands are going to be reporting the Rouse-Scott F test of the association between these 2 variables, adjusting for the design features. Okay, everybody with me? Questions about this? Anything?
Yeah.
Yep.
Here,
Yep.
we consider the age when it's less than 29.
Right.
But what about I have to run through these 2 lines again? Age when it's greater than 12 to get the same result as getting from state.
It's overkill. It turns out that in NCSR, 18 is the lowest age to begin with. So I didn't technically need the age greater than or 18 in Stata. I was just illustrating something there for the ampersand. So in NCSR, 18 is the minimum age value.
And also, there is a privilege for Stata and compared with R because we have standard error confidence interval because of
Right.
the design effect. So all of these words cannot be obtained from R.
They can, I didn't add them here for this example, so they can be added, like, if you calculate def. The problem is that we're using SVY by. So you'd have to do this using, survey mean is where you have the argument to use def. I don't have it in SVY by. So I'm using SVY mean as the analysis function. I could do this separately for each category of education in SVY mean if I wanted to. That's where I would get the design effects. I can't do that automatically in SVY by. So that's why I didn't do it in this particular case. But you could do it if you wanted to. You just have to run SVY mean over and over and over. So again, a little bit more work, but just the way that the R is programmed here. The key thing is that we want to supplement SVY by with the SVY chi-square to get that design adjusted test in the first place. Good questions though, for sure. Okay, let's look at what we find. So for this table, and this is an example from ASDA in chapter 6, each of the 4 categories of education, okay, you see 0 to 11, 12, 13 to 15, and 16 plus. So we have this mix of less than high school, some college, and then college and above. Those are the 4 education categories. We see the weighted estimates of these row percentages. So looking at those weighted estimates, it seems like individuals with less than high school education have the highest risk. But then there's like this U-shaped relationship, right? For people with high school or some college, they tend to have the lowest estimates. And then coming up to people with college, there's a little bit higher estimate. Again, kind of like this U-shaped curve showing this association. Row proportions, sum to 1, as we would see. So eyeball test seems like there might be an association. Okay, so let's look at our formal tests. The unadjusted Pearson chi-square based on the weighted proportions, so still using the weighted proportions, look at the p-value. Less than 0.0001. If we just implement the unscaled, unadjusted Pearson chi-square that so many people were using up until the 1980s, that would tell us there's a huge association between education and alcohol events. You say, oh, wow, this is great. You can write a paper, talk about why this might be, talk about why it's a public health problem, et cetera, et cetera. Okay. Again, reviewer of that paper comes back and says, oh, did you use the Rouse-Scott test or did you just use the standard Pearson chi-square? You say, oops. All right, I'll go see what that test says. Look at the Rouse-Scott F statistic. It's 1.64. That p-value, 0.18. There's no comparison. Even if you were to call 0.1 a borderline evidence of significance, when you adjust for these design features and these design effects engaging this association, there's no longer any evidence whatsoever. We went from something being significant at the 1/10,000th level to something with a p-value of 0.18 when we were properly accounting for these design features. That's why that Rouse-Scott work was so fundamental. People were ignoring these design effects and trying to quantify this association for so many years. Why is that happening? Look at the parameters of that test. We have a sample size of 1,275, that's fine. 42 degrees of freedom, that's fine. Look at the average design effect. It's 6.62. And that was being ignored in testing the overall association between these 2 variables. Furthermore, look at the coefficient of variation of the design effects, okay? The standard deviation divided by the mean. Standard deviation is half the mean, more than half the mean, okay? Then we're squaring that, and we're adding 1 to that. We're rescaling that factor. So even with a large mean, a lot of variability, we're still seeing a substantial correction for the design features that would have been completely missed in the naive chi-square analysis, okay? So when we use the Rouse-Scott test and we see evidence of a strong association, we're very confident. Then we can say, okay, we've fully adjusted for these design features, all these design effects, we still find evidence of this kind of association. But in this particular example, we could not say with any level of certainty that there's any evidence of an association in the larger NCSR population based on this kind of analysis. And again, you get those test statistics by default in this data. A little bit of extra work in R, but you'll still get the same result. Okay, so this is a really important example because it shows this difference of what can happen when you're ignorant about these design features versus when you account for them. When we start talking about looking at associations between variables. This is very important. Okay? It's nice that it's such a convenient test that we have available within, especially within Stata. Okay, questions about this example? Any questions here? Yep, Jupiter.
For the unadjusted Pearson square.
Yep.
Did it even not include any kind of weighting?
Yeah, the weighting, so that 27.21 is based on the weighted proportions. So that's based on the weights, right? So again,
So if we had not even weighted, then
we don't know. I didn't show it. I don't know what that would have been. But the weights, and again, I just can't emphasize this enough. This is why this class is so important. And I wish we could offer it to more people. The vast majority of people working with these data sets, they just plug in the weights and they say, I'm good. Just by plugging in the weights, I've accounted for all the design features. This is what can happen when you do that. That's not the full story about the complex sample design. In this case, adjusting for the stratification and cluster sampling is very, very important. Okay? Ignorance of that would lead to a radically different conclusion about this association. That's the key. Okay. Other questions about this example?
Great.
Yep.
After this test.
Yep.
I don't know if it happened a lot of reviews about the older publications.
What do you mean by reviews of the older?
Because people publish articles using unadjusted.
Yep.
Square.
Oh, you mean like people going back and
Yeah,
revisiting?
yeah.
Unfortunately, no, it doesn't happen a lot. I mean, we tried to do that, like I mentioned early on, like going back to older articles and seeing what methods were being used. That's what we found. But I mean, you know, my research team, what did we review? Like maybe 300 articles? There's so many more that are out there, you know, different fields, like, you know, it's disturbing. You know, and you know, somebody could go on a grassroots mission and say, I'm going to go back and call out every single author who's ever done. Nobody has the time to do that. It's just a comment how this can be very, very important. Because that's not like those people who are trying to be nefarious. Say, ooh, haha, I'm gonna ignore these design features just so I get a good result. They were doing what they were trained to do. They were using their best possible approach. They just weren't aware of these issues. So it's a challenging problem, but that's the key. Is that, and that's, you guys can be ambassadors and say, okay, this is how we got to go about this kind of analysis. Like, okay, other questions about this example or anything else that we've covered today with categorical data? Any other questions about categorical data so far? We're going to keep this discussion going for sure. So, other questions?
I assume that to get the similar codes for state, et cetera, just go to the website and download the example analysis.
For Stata, you said, sorry? The
Or
Stata
sorry, for
code's right
staff.
here. Yep.
Sorry, for staff, just go to the website, the book, and download the
Yeah.
chapter 6.
Yeah, so you'll see the code for proc survey freak there. You'll see the options for the second order Rao-Scott correction. You'll see all that on the website. Yep.
Perfect.
Yep. Other questions about this example? Okay, I think we're all set for today then. So again, we'll try to get back to you by Wednesday with homework number 2 feedback. I will try to get back to you today about your prospectus submissions. Looking forward to reading those. And let us know if there are any questions about homework number 3. Okay, so Wednesday we're going to talk about subpopulations. We're going to talk about quantiles. We're going to talk about looking at functions of estimates. So like t-tests and things like that. So additional bivariate analyses. So that'll be our discussion. Then Friday, we'll have a chance to practice with all this stuff in the lab. Okay. Okay. Thanks, everybody. I think we're all set for today. I will see everybody on Wednesday.